Hello and welcome to Cat World, the home of the world's largest self-filling water bowl. I mean ECE 205. ECE 205, not Cat World. We still have water bowls. Okay, so what are we going to talk about in today's lecture? By the way, the last lecture in the online format. Hey! So what are we going to talk about? Well, in the last couple lectures, we talked about how to compute Laplace transforms, right? So in the last two lectures, we learned two things. What were the two things that we learned? Well, the first thing was how to compute Laplace transforms of some function, right? So we could compute this thing here of f of t. And the other thing that we learned was how to compute the inverse Laplace transform of capital F of s. Okay, so for the direct computations of a Laplace transform, we could do that via evaluating those integrals. But for the inverse transform, since we don't know complex analysis, we were really stuck with just using the tables here. Okay, so we taught you new tricks. You've kind of noticed that these tricks are used in circuits, or at least some of you have via Piazza. And I will briefly talk about kind of the mechanism upon why this can tell you useful things when dealing with the circuit in our first in-person lecture. Okay, so we'll start with a little bit of a discussion on that you don't have to really take notes on, but you can ask all your questions and have a nice live interaction there. Okay, so now that we know how to compute Laplace transforms and inverse Laplace transforms, the next natural question to ask is, why did I make you do that? And the answer to that question is, because I could. Okay, end of story. Nope, done. Okay, no, but really, why did we go and learn these new mechanisms here? Well, it turns out that they're useful for solving differential equations. So what I'm going to do is start by stating two theorems from the text with the proofs, and then we're actually going to get our hands dirty. Okay, so in this case, it actually works best if I give you the theorem first, so that's why I'm doing it this way here. Okay, so now suppose f is continuous on some open interval, or half open interval, and it's of exponential order s naught. Okay, so the reason why we want to have this thing to be of exponential order s naught is so that the Laplace transform is well defined. Okay, so if you recall from our previous theorem on the existence of Laplace transforms, we needed exponential order for things to work out. Okay, further, we're also going to assume that f prime is piecewise continuous, where we introduced this idea semi-recently. Again, it's going to be piecewise continuous on this half-open interval. Then f and f prime have Laplace transforms for s greater than s naught, and this thing here is true. Okay, so the proof for this is pretty straightforward. I don't want to rehash everything that's in the text directly, just to save a little bit of time and keep this a little bit shorter. So let's just examine the proof and then talk about what the text does. Okay, so here's the proof from the text, and let's just briefly think about what we actually need to prove. Okay, so here I really have two things I need to prove. One, I need to prove that these Laplace transforms of f and the Laplace transform of f prime, I need to show that these things exist, okay? And to do the heavy lifting there, the only theorem we really have for existence is theorem 8.1.6, or doing things by definition. So here, since I'm dealing with arbitrary continuous functions of exponential order, that type of thing, I'm going to need that theorem 1.8.6. And the other thing I need to prove is this formula that the Laplace transform of f inverse of f derivative, that this thing is simply equal to the s Laplace transform of f minus my f naught. Okay, so these are the two things I need to prove. Okay, so we can do these in turn, and we could try to start by proving this in general, just by assuming that f is continuous and f prime is piecewise continuous. But it turns out that it's useful to split these up into two cases, and first consider the case where the derivative is continuous on 0 to infinity. So why is this the case? Well, if f is piecewise continuous, then basically what does that tell me? Well, if f is piecewise continuous on this interval, all that really tells me is that it's continuous outside a set of finitely many bad points, okay? So if I were to plot a graph of this, I could list these points, and there's finitely many of them where it's not continuous, but the key idea here is that there's a last point, right? So this is a last point where this function is bad, like behaves badly. Okay, so on this interval from, say, here off to infinity, or any closed interval that's kind of a subset of this, we know that f is continuous, or f prime is continuous. So from here, it can be useful to split up into these two cases, and it kind of can help us work through the problem. Okay, it's not strictly needed. You could start with the assumption that it's only piecewise continuous, and then go from there. It's just this way makes it a little bit more clear what's happening. Okay, so what do? Well, the first thing, we know that f is continuous and it's of exponential order, so immediately we know that it has a Laplace transform, right? That's just straightforward. So let's just make that statement here. Okay, so next we're going to consider the case where f prime is continuous, because it's a little bit easier. And what are we going to do? Well, we are simply going to try to find the Laplace transform, see what happens, get our hands a little dirty. Okay, so this thing, if I took the limit as t goes to infinity, would give me the Laplace transform. So I can start with finite t and take the limit. That just makes things a little bit convenient there. So the question is, how do I turn something like this, in the limit of course, into something that would look like this? Well, I need to get rid of the derivatives on f. How can I get rid of derivatives when I have a product inside an integral? Integration by parts. So here what's really happening in the background is they're saying dv is equal to f prime dt, and they're also saying that u is equal to e to the negative st. Okay, so if you do this, straightforward integration by parts, you get this stuff here. Okay, so now that you have this, direct computation over here gives you this thing here. So now our goal is to turn this expression here in the limit into this expression here. Okay, so you can notice pretty clearly I have a minus f naught, I have a minus f naught, that's all nice there. And then you could further notice that we have this extra term, this s, the integral of this thing, and you could say, hey, in the limit, this thing will go to the Laplace transform of f. So in the limit, this thing matches here, but we have this extra term that could be a problem, and that would be this term here. So how do we get rid of this term? That is the golden question here. Well, here's where we need to use the fact that f is of exponential order, right? So if t goes to infinity, we need to ask the question, what happens here? Well, since f is of exponential order s naught, then I know f of t grows like, so I could use this notation here, little f of t, I know this thing acts kind of like some constant e to the s naught times t as time gets large. Okay, that's what exponential order means. So if I make this substitution in here in the limit, which I can do because I'm taking a limit, then I end up with an exponential of s naught minus s. Okay, so in this case, if s is bigger than s naught, that will go to 0. Otherwise, that will diverge. Okay, so from here, that's why this thing is going to 0. Okay, so this exponential order stuff, this is telling me that f looks like that when t is big. Okay, now from there, if I just plug that in, straightforward, taking the limit gives me the result that I wanted for this case. Okay, so for this case, I've proven two things, right? I've already proven that Laplace transform of f is defined for all of these f's. There's no problem there whatsoever. But I still don't know whether or not this f prime exists. So here, by actually computing a Laplace transform that's defined for various values of f, I've guaranteed that the Laplace transform exists within this case. Okay, so if you want kind of broad, overarching ideas of the proof, this up to here is really proving it in the case where f prime is continuous. Okay, so now with this kind of in mind, we need to see what happens or what changes when f prime is no longer continuous, but it is instead piecewise continuous on some set. Okay, so here, if we assume that this f prime is piecewise continuous from 0 to t, with these discontinuities at t1 up to tn, so finitely many of these guys, for convenience, we could just say that my t0 is 0 and my tn is n, and our t, and these are not discontinuous and f is not discontinuous at these points, then what I can do is repeat the same trick that I did before, but I want to integrate it on one of these intervals, right? So basically, what can go wrong in the case when f prime is piecewise continuous but not continuous? Well, if you remember what piecewise continuous functions look like, just kind of a canonical example, if I went, say, from 0 up to infinity, instead I had these two bad points, a piecewise continuous function would be something that might look something like this, and it could go down to here. Let's fill that in and make a circle up here. Could do something like this, okay? Canonical picture. So what's happening here is above this bit, I'm fully continuous. So basically the work that I did up here applies and nothing bad happens. But the issue is that in between there, going between the 0 up to this point where I no longer have any more discontinuities outside of it, that's where problems occur, right? So here we basically need to contend with this idea that at these jumps, and at the endpoint over there where I have another jump, bad things could happen and we might not be able to evaluate the integral. So our goal is basically to evaluate the integral from 0 up to t, where this point t is at the point where beyond it I have no more discontinuities. So if I can evaluate this integral of f of t e to the negative st dt on this interval here, then I'm guaranteed that the Laplace transform will exist. Okay, so for the purposes of notes, basic idea for why I need to consider the cases. Okay, so here basically what you're doing is you're evaluating this integral on one of these regions. So you're finding the area between an arbitrary one of these sections like this, and integration by parts simply gives me that it's going to be this expression here. So then what you do is you add all of these bits up for all of these little regions, okay? So you basically compute this region here, and keep picking them for all of the little regions in the middle, add them together. So that will give you a finite area all the way integrating up to this point t. And then when you go to take the limit, since f is continuous outside of this region here, you end up getting the other result following directly. And a key idea in here is that these little elements here actually collapse on each other, right? Like if I take this thing and I add it to the next term, to the next term, to the next term, etc., if I add up all those little contributions from these areas, ignoring this integral bit here, then they end up just being this thing here. And at the end of the day, when t goes to infinity, this goes to 0, argument that I did earlier, this stays exactly what it is, and I'll be left with this extra integral here that when I add all of it together, that'll give me the integral from 0, or from t all the way up to infinity, which gives me what I need, or sorry, from 0 all the way up to infinity in this case, which gives me what I need, okay? So that's how the piecewise case there works. Don't particularly need to know that particular proof, but it's good to be able to derive that and know where it comes from. Okay, so this is how to handle first derivatives. And luckily for us, there are no equations that ever involve a second derivative. So this is all we need to know, right? Well, no, there are second order differential equations. We do care about them. So let's actually examine them here. Okay, so if I look at one more theorem that I will state and go through the proof, then we will get into some of the nitty-gritty of how to actually use this, which is the practical thing for this lecture. Okie dokie. So here, suppose f and f prime are continuous. So now I have that both of these things are continuous on this half open interval, and both of them are of exponential order s naught. And now I'm going to say that the second derivative is piecewise continuous. Then it follows that f prime, and f double prime all have Laplace transforms, and the Laplace transform of f prime is exactly what we found before, right? So this is really what we found in theorem 8.3.1, right? And it further follows that this is what the second derivative looks like. Notice that the only things that really changed is that we now have a square, and we now have an extra initial condition, and we now have an s sitting here, okay? Nice things happen. So let's look at the proof of this real quickly. Okay, so the basic idea is that we're going to rely on theorem 8.3.1 to handle all of the stuff with this first point here. So basically, from there, we know that the Laplace transform of the derivative exists, the Laplace transform of the function exists, because, and that it would satisfy this expression here for s greater than s naught. Pretty trivial. Now, to prove that I can take this Laplace transform of f double prime, all I have to do is go back to this previous case here and let f replace f prime and let f double prime replace f, right? So if I do the substitution where g is equal to f, then my g prime would be f prime prime, reapply that theorem, and from there I can get what the Laplace transform of g prime would have to be. But g prime is again f double prime, so from there I can do this replacement where I replace f with g, or g prime with f prime double prime, and once I do this I get this expression here, but at this point I don't know what the Laplace transform of f prime is, so I take this thing up here and I just plug it in. Pretty trivial. Okay, I would highly recommend memorizing this and memorizing this. Okay, so really you just have one theorem to memorize, but if you really are only going to memorize one of the theorems with what conditions you need on the function, I would recommend memorizing 8.3.1 because you can derive other things from it. Okay, one note here, we can generalize this to work for arbitrary ordered derivatives. Okay, so if you want to go really hardcore math, you can actually use induction to find a formula for the Laplace transform of f to the n, assuming that f to the n, where n is the nth derivative, is piecewise continuous, and all of the lower order derivatives are continuous on that interval. Okay, so you could do that. We're not going to do that. So now let's get our hands dirty and look at how we can actually do stuff with this. Okay, so for our first example, we're just going to solve this differential equation. Now, note we already know how to do this, and we have a method, but there are other differential equations that get kind of messy, right? So this is more of a demonstration of how things work here. So what can I do? Well, I could try to solve it using the old method, but let's try using a Laplace transform to do this. So what we're going to do is we're going to say let capital Y of S be equal to the Laplace transform of y of t. Okay, so this is our little notation thing. So now what I'm going to do is I'm going to take the Laplace transform of both sides of the equations. Or if you want, you could think of it as a kind of mid-step where you could just rewrite this by multiplying by e to the st. This is perfectly allowed to do. This thing's never zero, so we're not collapsing our solution and losing information. And then you can integrate with respect to t on both sides from 0 up to infinity. Okay, so here we're doing the Laplace transform of each side. Okay, so using our kind of better notation for the Laplace transform, this is really saying I am computing the Laplace transform of y prime, and I'm setting it equal to the Laplace transform of a y. Okay, so here the result of the Laplace transform are well defined, so I can freely do this, but if you want the details, we're really doing this as an intermediary step, and this thing you don't necessarily have to do in homework if you want. Okay, that's just a demonstration here. Okay, so now that I have this, how do I simplify this problem out? Well, I have the Laplace transform of a derivative. If only I knew how to compute the Laplace transform of a derivative. Well, I do. I have that theorem 8.3.1 or 8.3.2. You don't have to cite the theorems in your homework, but they're a thing. So here I can say, hey, the Laplace transform on this side is just s, the Laplace transform of y, is equal to, minus my y evaluated at 0. Oh, that is my initial condition. That's handy. And now on the other side, this thing, I can pull out the a outside of the Laplace transform to rewrite it like this. Okay. So now if I want, I can use my definition of y that I had up above, where this capital Y is this Laplace transform, and I could rewrite this in terms of my capital Y. Okay, so if I do this, I could say, hey, this is a algebraic equation. It was a differential equation, but now it's not. But this is now an algebraic equation for capital Y. That's amazing. I just took all the calculus out of calculus, right? There's nothing else, or out of difference equations, right? There's no calculus sitting here. There is, it's hidden in the Laplace transform, but I can freely solve this for y sub s. Just algebra, right? Things are nice in this, quote, frequency space. So from here, I can solve this just pretty directly, just doing some algebra, and I can find that my capital Y of s, what's that going to be equal to? Well, I'm going to have my y naught, so my y sub 0 is just generally y naught, or in this case, explicitly y naught. And this would be divided by what? Well, I'd subtract off the a and then divide by s minus a, so s minus a. Okay, so now I know what y sub s is, but I don't care about capital Y sub s. I want little y of t. Well, how do I undo it? Well, simple. Y of t is equal to the inverse Laplace transform, our friend Mr. Inverse Laplace transform, of this capital Y sub s. Well, this is just the inverse Laplace transform of y naught over s minus a. Okay, and we have tables. We know how to compute this. We pull the y naught out, and then we simply get the Laplace transform of something that's of my form of an exponential function, right? S minus a. So here, at the end of the day, once the smoke clears, this is simply y naught e to the a t. Okay, so I have solved this initial, this initial value problem without ever actually having to compute a derivative. That's handy. That's useful. That's, for this course, why we care about Laplace transform. Okay, so now there's other reasons why Laplace transforms are useful. It's always going to be useful when you have a linear system. If you take the Laplace transform of it, it allows you to talk about the eigenvalues or eigenvectors, or potential eigenvalues, or eigenvectors, of the system, and just kind of properties from linear algebra make nice things happen there. I'll talk about that in class. But yeah, here's why we care. So let's look at another example of doing a second order differential equation. Okay, so now let's examine this example here where we want to try to use the Laplace transform to solve this differential equation here. So note, we already know how to solve this. We could find the complementary, or the solution to the complementary equation. Then we could use that to pick an ansatz to try to find a solution to the forced equation. And then after we do that, we add them together and apply our boundary condition, our initial conditions, and hope that at the end of the day, everything works out well. Which it would. This one's not a particularly bad problem to solve, but instead of doing it that way, let's use our new toy. Okay, so if I take the Laplace transform of everything, what happens? Well, here I get the Laplace transform of y double prime, okay, minus. So here I can pull out the 6 out of this bit of the Laplace transform. So again, note here I am using the linearity property to split the left-hand side up here. And then finally from here, I can get a 5 Laplace transform of y, okay? And on the other side, I simply get 3 Laplace transform of e to the 2t. Okay, so here we really just are hoping that this is something that's in our tables, so we can just evaluate it, which this one is. Okay, so now what we want to do is evaluate all these Laplace transforms here. So in general, you can feel free to always redefine this capital Y to be the Laplace transform of y, so let's do that here. Okay, so I can say y of s is going to be equal to the Laplace transform of y, no primes, of t. Okay, so I'm just going to do this thing here. So from here, if I do this, then I can use my properties of the Laplace transform to write this out. So you don't have to state the theorem. You could just freely jump in and do it here. But what you can do is note, hey, the Laplace transform of y double prime, I know what that thing is. This term will just be s squared times my capital Y of s. Okay, then I'm going to have a minus little y prime of 0. And this term here isn't multiplied by s, and then I have this extra minus s y of 0. Okay, so this is just this big Laplace transform here. So then I get minus 6, put big parentheses, and I can use the fact that I know what the Laplace transform of y prime is from that theorem 8.3.2. So here what I can then say is, hey, this term is just going to be s times capital Y of s, pretty straightforward, minus y of 0. Okay, and then I can put my closing brackets right over here. Okay, now here 5 times this Laplace transform, well, that's just 5 capital Y of s. Okay, this is equal to, well, what's the Laplace transform of e to the 2t? Okay, so if it's not in the tables, you need to do it from scratch, but if it is in the tables, you can just tell me from the tables we get blah. So here I'm going to use bad notation and say table. And from the tables, Laplace transform of e to the 2t is just 1 over s minus 2. So this is just 3 over s minus 2. Okay, so it's critical to either memorize the Laplace transforms or learn how to use the table. Okay, so now what I can do is I can go back to my question. I had initial conditions, right? So let's use this and clean up this problem a bit. Okay, so here I have a capital Y sub s term sitting here, and I have a capital Y sub s term sitting here, and one here. So if I combine all of these terms together, I could simply say, hey, I have s squared minus 6s plus 5. And all of this is multiplied by my capital Y of s. Okay, and now I have the rest of the terms to deal with, and these rest of the terms either are initial conditions or involve some functions of s over here. Okay, so let's just chase this thing out. So here, since my y prime of 0 is 3, this simply becomes minus 3 from this term. This becomes a minus 2s. This term we already accounted for here. This term becomes a plus 6 times, or positive times positive. So then I get 6 times this term here, 2. So just a 12, and that's coming from this term here. So for future reading people, I will highlight that to make it a little bit easier to see where that comes from. And then this term's already gone. That will simply be equal to 3 over s minus 2. Okay, so now my goal ultimately is to solve for this y sub s term, but there's kind of a problem with that. In order to do it, I'm going to have to take a Laplace transform of everything else that I have to deal with. So you could blindly do algebra and put yourself in kind of a really bad position to try to solve things out, or you can think cleverly and try to make the partial fraction steps a little bit easier. So let's do this the clever way. So this thing here, ultimately I'm going to add all of this stuff over, well, add or subtract it to get it to the other side, and then I want to divide by this. So for partial fractions, it's useful if I have everything kind of factored out. So what I'm going to do is I'm going to factor this term. So I could rewrite this as s minus 5 times s minus 1. So in kind of toy homework problems, these will easily factor, but in some real world questions, they might not. So just keep that in mind. Okay, so now what do I do? Well, I can pull all of this stuff to the other side of the equation, so I can say this will be equal to 3 divided by s minus 2 plus all of this stuff here, right? So we could just blindly move these terms over here. Okay, so the book noticed that there's a nice little trick to be had here. I'm going to ignore the trick. So if I take the 3 and I add it to this, what do we get? We get a 9. So here I'll have a minus 9, but I'll get this plus 2s minus 9. Okay, so now I want this ultimately to be convenient if this is one big fraction, right? It'll help me to avoid from having to do partial fractions multiple times here, right? Because if I leave it like this, I would have partial fractions here and partial fractions here, whereas if I combine them, it's just one big expression. Okay, so how do I combine them? Well, I need to multiply this thing by s minus 2. Okay, so what I can do here is I could rewrite this whole thing as s minus 2. Here I would still have my 3, and here I'd have a plus this term, 2s minus 9 times my s minus 2. Okay, good stuff so far. So now what I want to do is solve this for y sub s. So now I can just simply divide everything through by my y, or by the term in front of the y sub s. Okay, so here I get capital Y sub s. This will simply be equal to all of this divided by these terms here. So first montage music of the day. Okay, so I've now solved for y sub s, so good things have now happened. Okay, so now that good things have now happened, what I need to do is do some partial fraction decomposition stuff. Okay, so the book skips it. I'm going to skip it. You should know how to do it from that lecture where I chased out all the details for partial fraction decompositions, but TLDR version of it, what you would simply do is you would assume that this would be something of the form constant divided by each one of these terms. So constant divided by s minus 2 plus constant divided by s minus 5 plus, b, plus constant divided by s minus 1. Okay, so then with the assumption that this is of that form, you could either apply Heaviside's method, which I would prefer you do, it's a bit cleaner, or instead of doing that, you could just simply chase it out and get an algebraic system and solve it. Heaviside's method will save you algebra, so I suggest doing it. But at the end of the day, after you do that, you simply get that y sub s can be written in this form. Okay, so montage. Okay, so now this is of the form of something that I can take the inverse Laplace transform of. So I can simply say y of t. Well, that thing is just going to be the inverse Laplace transform of capital Y of s. And this will be, well, if I compute the inverse Laplace transform of this, if you want to be super formal, you could write out and now we can compute these individual bits here. So in practice for your homework, you can feel free to jump from the top line to this thing here. You don't have to explicitly invoke linearity. I'm not going to require you to do that. But then I do want you at the end of the day to state the table. So from here, this is from the table. Okay, it's pretty straightforward in this case. They're just exponentials. So since it's simplistic enough, you can just write them out. But if it's something like sine or cosine or e to the x times sine or cosine or t times it, I would like you to actually say, hey, I looked at this bit in the table and that's how it worked out. Okay, so from here, we could simply just compute all these Laplace transforms. This one will be minus e to the 2t. Here, this one would be 1/2 e to the, in this case, 5t. And for this last case, we'd have 5/2, and this would just be e to the t. Okay, so here, this is our final solution for this problem. Okay, so pretty straightforward, and you really have your options now. If I don't tell you how to solve something, then you can use Laplace transform or the previous material we've done. It's just your choice of if you want to deal with the partial fraction stuff or chasing it out via our previous methods. Okay, pretty straightforward, I believe. Okay, so I'm going to keep this lecture short and to the point. We're going to do one more example. If you want to see more examples, you can see it worked out in your text, but really, after you've seen a couple of these, it's just kind of algebra management and keeping track of things. So let's look at problem 6 from assignment 1, okay? So this was the difference equation to model Marmy's water bowl. Okay, so if we wanted to solve this by using Laplace transforms, the first thing we would do is take the Laplace transform of everything here. So I would like you to write it out as what you do. So here we take the Laplace transform of this w prime prime plus 4 Laplace transform of w. Okay, and to this would simply be equal to the Laplace transform of e to the minus t and plus the Laplace transform of 1 with a 5 on the outside. Okay, technically you could do Laplace transform of 5. It works out just the way you would expect. Okay, so here if we do the arithmetic, what happens? Well, this w prime prime, that gives me a term, this s squared, the Laplace transform of w, okay, minus w prime of 0. So that's going to be my initial condition up here, minus s w of 0. So that's my initial condition over here, plus, so here this will stay as it was for Laplace transform of w, nothing fancy there, is equal to, well, what's the Laplace transform of this? Well, if you go to the tables, this would be 1 over s minus 1, or plus 1, and here, just tell me table. Okay, this one is this direct, straightforward thing that's from the table, so do it. If it was like sine or cos or something, maybe just off on the side, say the rule that you're using, right? So yeah, it's kind of up to discretion there, but do tell me where you're getting these from. If it's directly in the table, duh. If it's not directly in the table, you can't freely write it out, okay? So that statement there is mostly for academic integrity. I don't want you saying Laplace transform of complex thing is this little thing here. If it's not in the table, explain how to make it into something that is in the table, and if you can't do that, do it by definition. Okay, nevertheless, here, again, this is 1 via the table, because Laplace transform of 1 is just 1 over s. Okay, and again, notice here I'm not actually stating my domain of s. I don't care about the domain of s for this context of this problem. I just care about the solution to the original thing. I'm just visiting S space for a little bit. Okay, so now you could do the thing where you call this Laplace transform of W capital W. That's a personal choice based off your thing, but for this context, I'm not going to do it. So we're going to do the same thing that we did previously where we want to kind of simplify this out. So let's just notice something here. And what is the thing we're going to notice? Well, there's only 2 terms here, this term here and this term here, that have a Laplace transform of W. So we're just going to combine all these things in a nice way. Okay, so here I can notice this is going to be s squared plus 4. So that has roots in the complex plane, and thus it doesn't simplify. So we're going to be stuck at the end of the day with s squared plus 4 in front of our Laplace transform of W, the thing that we want to actually find here. And again, squiggly brackets, not round brackets, okay? So unfortunately, we can't simplify this out, but we do know how to go about applying partial fractions for things of this form here. Okay, so what else can we do? Well, we could say this is equal to, and we're going to clean this side up in a second, but 1 over s plus 1 plus my 5 over s. Now I want to pull these 2 terms to the other side of the equation. So how do I go about doing that? Well, that's a simple addition. Okay, so I'm also going to do something else at the same time. I'm going to take advantage of the fact that this thing is this thing, and this term, or sorry, opposite way, and this term is this term, I had it the right way, and that other term is this term here. Okay, so if I plug in this initial condition at the same time that I bring these over, here I'd have negative 0.2, so that's plus 0.2, so minus 0.2 here. And here I'd have negative this, so when I add it, I'll get a plus 2.68 times s. Okay, so now I want this to be one giant fraction to make my partial fraction stuff a little bit easier to handle algebraically. Mathematically speaking, you don't have to do this, but it will make your life a lot nicer than doing 4 potential partial fraction decompositions, right? So here, if I chase out the details, here I'm going to get a common denominator of what? Well, here I have s plus 1 here, and I have an s here, okay? So to get this term here, I need to have a 1 times s, or just s, sitting here. To get this, I have to have a 5 times s plus 1. And for these 2 terms, I need to multiply them both by s and s plus 1. So here I'll simply do a minus 0.02 s times s plus 1. And here I'll get a plus 2.68 s squared s plus 1. And again, I'm not factoring these out because having it in this form will be useful for partial fractions. Okay, and finally, let's clean this up a little bit further by noticing that this term, this term, and this term all have a s plus 1 in common. So, and these two terms here have an s in common, and that'll let me make things a little bit cleaner algebraically later. So let's rewrite this one final time. This would be s times s plus 1. The order doesn't matter. Here, I'll leave the s alone. Plus, in this case, I have a s plus 1 times what? Well, here I have a 5. Plus, both of these terms now have an s in common. So I can do plus, factor out a term of s, and what's left? Well, after I pull out a s plus 1 and an s out of this, I have minus 0.2. So I'll put this minus 0.2 here, just for convenience with the plus signs. And here, I'm left with a 2.68 s. Okay, so having it in this form will make it quite a bit easier when I actually go to compute the Laplace transform for plugging in values of s. I can plug in here, kind of work my way out. Okay, you don't necessarily have to do this. It's a choice. Okay, so now I'm ready to actually isolate for this term here. So when I do that, I simply get what? Well, the Laplace transform of w prime, or w, no prime. There we go. Let's clean this up over here. Okay, this term would explicitly be this expression here. Okay, so now if I want to actually evaluate this thing here, I now need to do my partial fraction decomposition stuffs. Okay, so let's do this here on the side, and let's actually chase out the details here just to give you an example of what I mean by algebra management. We've already done some algebra management by just kind of cleaning this side up and putting it in a convenient form, right? You could have left it as this form, but it's going to get god-awful once you go to chase that out. So here, I'm going to call this thing here, just for convenience, I will call that capital F. Okay? So here we want to do the partial fraction decomposition of capital F. So what would this be? Well, here I have three terms. So the first term is just a single s, so we get this. The second term is, oops, not one, a. The second term is just this 1s plus 1. So from it, we're simply going to get b over s plus 1. And this last term is a quadratic. So if you recall from a quadratic, we need to guess cs plus d for this quadratic term here, which yeah. Okay. So now what I want to do is chase this out. You have options. I am going to go through and do Heaviside's method because I don't want to try to multiply this out and get a god-awful system of equations. If you were wanting to do it via the system of equation approach, actually doing the simplification here would kind of hurt you as opposed to just expanding out the top. Okay, so here if I do this approach, what would I go about doing? Well, I would say if s is 0, what happens? Well, in the case if f at s is 0, I would ignore the factor of s here, and I would simply get a is going to be equal to all the stuff over here where I ignore this s. Okay, so in this case, this is pretty simple to do. So I'll write it out for this case. I get 0 plus, here I get 0 plus 1. That's just going to be 1, right? Here I get 5 plus 0. This is why it's nice to write it in this form, because this s cancels out this term. I don't have to worry about computing this thing here, right? It saves me that work of a little bit of algebra, okay? And on the bottom, what happens? Well, I just get 0 plus 1 times 0 plus 4, okay? And I do recommend showing this work here common thing is doing algebra errors, and if you show your work, we can identify whether it's algebra error or whether it was your fundamental misconception, and we can give you more partial marks. Anyways, from here I get 1 times this 5, so that is just a 5 from there. In the bottom I get 1 plus 4, or 1 times 4, so this is just a 5 over 4. Okay, I now know what A is. Okay, so now my next goal is to make a guess for B. So what's the appropriate guess to make the B term work out well? Well, if we look at it, this is a s plus 1, so if s is equal to minus 1, this term here vanishes, and via the Heavisides method, I simply take this thing here, plug in 1, and then I plug in 1 into the or negative 1, and then plug in negative 1 into the bottom, where I ignore that s plus 1 term. Okay, so to save a bit of time here, instead of writing it all out, let's just use our handy dandy copier. I want those extra bits. Okay, well, fix that. Copier, paste it down here, and I'll do it off camera. We're not doing it live. Okay, so from here, what happens? Well, I would get B is simply equal to this thing, where I ignore this bottom term here, and I plug in my minus 1. Well, nice things happen, right? So this s becomes a minus 1. This s becomes minus 1, meaning this term is 1 minus 1, right? That is 0. So I don't have to do anything here, and I get to, since I copied it over, I get to erase all of it, okay? That is nice and handy, right? That's why I wanted it of that functional form. If you always try to put something in that form, nice things will happen. Okay, what am I left with down here? Well, I have a negative 1 multiplied by negative 1 squared, so 1 plus that. So if I chase out these details, this is negative 1 at the top, negative at the bottom, so those cancel, and it will simply be 1 over 5. Okay, so now I know what my B is. And again, this was easy precisely because I did this work to put it in this form. If I didn't do that, I was going to have a bad time. Okay, so now what do I want to do? Well, I want to compute what C and what D are. Well, to do this, I really need 2 equations, okay? So what I'm going to do is plug 2 different values of S. What value should I pick? Well, if you look up here, I've kind of ran out of a lot of the nice numbers. I could, if I wanted, use S is equal to 0.2 divided by this 2.68 term here to try to get this term to cancel, but that makes everything else even harder to deal with. So I'm just going to pick random numbers. It really doesn't matter, just something particularly nice. So I use 0 and negative 1. I could use 1. 1's a nice number. And I could use, say, 2. 2's not horrible to deal with here. So that's what we're going to do, and let's chase out these details in kind of speed mode. Okay, so now I just need to add all this together to get an equation for C plus D. So let's just kind of do this in a kind of quick way here. So if I take 5/4 plus 1/10, what would that be? Well, Mr. Paint's friend, Mr. Calculator, which you are allowed to use, tells me that that is just 1.35. Okay, so I have that plus the C plus D over 5. I might as well leave it as it is for now. That whole thing has to be equal to this. Okay, so you can evaluate this pretty quickly by working from the inside out, or you can just throw it into a calculator. In either case, you end up finding that it's simply 1.596. So if we chase this out here, I get this term here. Okay, so if you clean this up further, you can multiply everything through by 5 to get rid of the 5, and you could subtract off the 1.35 times 5. So if you do this, we find that our equation is simply c plus d is equal to 1.23. Okay, and the decimals here are kind of the annoying thing to deal with because we have these decimals from our initial conditions. Okay, so now I need to pick a different value here. So previously I suggested 2. So let's just stick with that here. Okay, so here, since I have the luxury of doing this in a digital setting, let's just copy this whole expression here and replace the ones that I wrote with 2's. That's why I was explicit in how I wrote it. So doing this, ends up changing here. Well, this 5/4 came from 5/4 divided by s. So if s is now 2, this term would be 5/4 times 2 in the bottom. Okay, and this 1/5, where did that come from? Well, that 1/5 was 1/5 times s plus 1. If we go up here, the b coefficient times this s plus 1. So in this case, this 1/2 would simply change to a 1/2 plus a 1 in the bottom here. Okay, so now this term here, what changes here? Well, this thing, again, was my cs plus d divided by this thing. So here, my s will change this to be a 2c plus d, and I'll get 2 squared plus 4. Okay, so here, if I change this out, I need a 2 in front of the c, and I need an 8 in the bottom. Okay, so I'll have an 8 here, and I'll have a 2 here. Okay, so from here, what changes over here? Well, pretty much all the 1's, other than the 1 here and the 1 here, become a 2. So just cleaning this up real quick. We get this expression here. So just double checking that we copied it all right, because I am doing this raw as I would be going through it as a student. So 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, perfect. Okay. So now what we need to do is we need to evaluate this out. Okay. So just doing things in Mr. Calculator, and just to show you some tricks that you can use here. Previously, when I went to compute this side, I knew that I wanted to do it more than once because I had 2 expressions to evaluate. So I just used Google's calculator. So here, if I tweak this out, I can rechange this out and change these 1's to a 2. Okay, just pro tip, you can do this on a regular calculator. I don't personally own a regular calculator anymore because I use them so seldomly. And I didn't feel like throwing this in MATLAB or Drive or any other software to do the arithmetic. So here we go, live demonstration. I get this awful number here with these repeated 6's. Okay, so the idea is here with these repeated 6's, this will probably cancel out. I do not want to round digits, right? Because unless I tell you to round things off, you should not in this course. So here, I would either need a calculator that would keep all the digits in this case, or I could just do this with a bar, okay? Everything here is going to stay rational because I started with rational numbers. Okay, so next I want to compute this thing here. So a direct computation gives that these 2 terms, when I add them together, is simply 0.6916 repeating. Ooh, that's nice. And it turns out that this is exactly, or this is nice here, precisely because we had nice things earlier, basically in this problem, okay? So here, these 6's will have a nice little thing happening with them. Okay, and then here, I'm left with the 2/8 and the d over this, so I can just simplify this out to say plus. So here, I could leave it as it is, actually in this step, because it'll be a bit easier to get rid of the 8. Okay, so now that I've kept all these digits, it's just converting this into an equation, so I can use linear algebra to solve this. Okay, so if I take these things that I have before and I multiply, like take this thing, subtract this off from it, and multiply it by 8, my repeated 6's go away. Okay, so from here, if I do that, I would end up with a 2c plus d is equal to 2.46. All the badness went away. Okay, so as a side note, if you wanted to be careful and avoid this badness to start with, the badness is really coming from the fact that I'm dividing by 8 here, and I'm dividing by 8, a factor of 8 here. So you could have, if you wanted to, I didn't, but you could cancel this term, this term, this term, and add in a factor of 8 over here, and that would get rid of all of those repeated decimals. Okay, it's your choice. This is kind of a dirty problem to do with Laplace transforms, which is why I'm picking it, so you can see real world what happens. But here, in either case, you need to keep all the decimals, so you can do it algebraically, use aid of a calculator like I did here, or just multiply through by 8. Okay, those are your choices here. Okay, so now what have I done? I have two equations here for this and this. So I can simply solve this pretty easily by adding them together or subtracting them together and then taking another scalar addition of them. Okay, so from here, it's pretty simple to say, oh, if I subtracted these, I would get, say, C plus D is equal to 1.23. I would subtract from this 2C plus D is equal to 2.46. Okay, so if I do this, here I get negative C. The D's go away is equal to, well, when I subtract these, mental math just tells us that this would have to be minus 1.23. You could use a calculator if you wanted. It's your choice, but it's minus 1.23. Okay, so from here, we can solve this for C, and we now know C is 1.23. Okay, that was nice and easy. And from here, we could use either of these equations we want to solve for D. And I'm just going to use this equation here. So this tells me that 1.23 plus D is equal to 1.23, which tells me D is 0. So there is no D for this case here. Okay, so here I'm just going to bracket this off. There we go, and that's all my work to find C and D. Okay, so what have I done? I found A, I found B, and then I've had to deal with this system of equations with a little bit of work here and some aid of a calculator to speed up the process, but I managed to find C and D. Okay, so I put all this work together. I know that this function f is simply equal to 5/4 over s times my 1/5 s plus 1 plus my factor of 1.23 times s, times s over s squared plus 4. Okay, so if I put this together, what I now know is that the Laplace transform of the thing that I wanted to find, so this Laplace transform of my w of s, inverse Laplace transform. Laplace transform because I never introduced the capital W. But we know that this thing would have to simply be equal to that f function. So that would be 5/4 times 1 over s, which we know the Laplace transform of 1 over s, that's just e to the t, right? Plus, what's the next term? Well, the next term that we had was this, and I lied about the transform there, but I'll fix that in a second. The second term that we have would be this term here, the 1/5 times b over s plus 1. This is the exponential. The other one's a constant. So 1 over 5, 1 over s plus 1. So that'll give us a decaying exponential with the power of negative t there. And then the final one would be a plus 1.23. And this will all be multiplied by my s over my s squared plus 4. Okay, so now if I want to find w, I just take the inverse Laplace transform of both sides. So here I would get w, if I want, is equal to the inverse Laplace transform of the Laplace transform of w. And this will be equal to what? Well, here, this just chasing it out kind of in the natural way, 5/4, the inverse Laplace transform of 1 over s, plus, so here I get 1/5, the inverse Laplace transform of 1 over s plus 1, plus here 1.23, the inverse Laplace transform of s divided by s squared plus 4. Okay, so now if we go to our Laplace transform tables, all of the elements that I wrote here are the standard elements of those Laplace transform tables. So if I just pull it over here real quick, so if we chase this out, and yeah, there we go. So here, this first one, the 1 over s, its inverse Laplace transform would be a constant. So here, just from the tables, we know automatically that this thing is 5 over 4. This next one from the Laplace transform, that's the Laplace transform for an exponential, right? I have s minus a. Here's a is -1. So this gives me a decaying exponential 1/5 e to the minus t. And finally, this last term, I'll get a 1.23, which I'll go ahead and write down. Here, what do I get? Well, in this case, I have this Laplace transform of that form. So if I find my cosine, here we go. That's just cosine of 2t. Okay, so this times cosine of 2t. Okay, this is my solution to the initial value problem. Okay, so basically with Laplace transforms, because when I go to evaluate that Laplace transform of the derivatives, when I go to do that, I end up getting those terms that depend on the initial conditions. I don't actually have to apply the initial conditions at the end, just like we saw before. Okay, so I claim this is A1 question 6, and I claim this is the answer to A1 question 6. Well, is it the answer to A1 question 6? Well, if I open up A1, so here we go. There we go. And now if I scroll down all the way down here to Marmie's question, what did we find for our solution? We found this was the solution. Ah, they're the same. Okay, so it's your choice of which one is more work, whether you want to do this or whether you want to do this process here. But at the end of the day, Laplace transforms are very powerful, and you can basically use Laplace transforms to turn any linear first order or linear nth order differential equation with constant coefficients into a problem similar to this. And as long as the forcing terms have nice Laplace transforms and the inverse Laplace transforms are nice, which generally speaking, if you start with a forcing term with a nice Laplace transform, things will probably stay nice. There's not a proof that they'll stay nice. Like you can get counterexamples, by the way. But generally speaking, as long as things are nice to take Laplace transforms of, this method won't be too bad. It's a bit long, it's a bit messy, but that's kind of how math works here. Math isn't always cute, so give an example here. Okay, so for your assigned reading, I want you to read this section 8.3. There's a bunch of examples I did not go through. Basically, I wanted to keep this short for your last online lecture, especially when you have 4 lectures to watch this week. And you definitely need to watch this lecture before the in-person lecture, so if you're not hearing this, then that's a bad thing. But anyways, so I want you to read section 8.3, look at those extra examples if you want to see more examples worked out, and here's a bunch of practice problems. Okay, so now for your meme, when we go in person, I'm going to be doing things on board, that type of thing, rather than lecture slides. So we really won't be able to give you memes, so let's just give you meme overload. Okay, Laplace transform meme. All of these are pretty much good. Well, most of these are pretty much good. So here, you can't simply compute the inverse Laplace transform. Yeah. Laplace transform in basic math. Yeah. Basically, all of these are good memes. So internet's your friend. I couldn't just pick one and wanted to give you meme overload. So yeah, Laplace transforms don't always work, but it's definitely worth getting a tattoo of. I don't have tattoos. I have no plan on getting a tattoo, but if I were, yeah, anyways. So, yep, I hope you all have a good last week, last Friday, good move-in weekend to prepare for the midterm, well, prepare for online classes and going into the midterm, all that good stuff. And I will see all of your smiling, masked faces on a couple days from now.